In this video, we're going to explain linear regression. You might have heard this before in like a stats class or an intro to AI class. Maybe the explanation didn't make a ton of sense, but in this video, we'll explain exactly what you actually need to know and skip over the unnecessary math proofs, and we'll even explain what you would need to know to code it up from scratch in Python. Linear regression is actually really important. It's the foundation of neural networks. It's okay if you don't know what these are yet. We're going to get to that soon. Linear regression is actually the foundation of all the latest AI and deep learning, like ChatGPT, self-driving, deepfakes. So it's definitely really important to understand. And let's jump into the explanation. Now let's break down what this term means. Linear regression. We'll start with the regression part. So regression is just the opposite of something called classification. So let's say we wanted to build a model that predicts whether or not someone gets diabetes. There's only two possible outputs, right, for this model. They either get diabetes or they do not develop diabetes. So anytime you have a fixed number of classes that your input could belong to, let's say you were building an image classification model that predicts whether or not the input image is a dog, a human, or a piece of food, right? There's still like a fixed number of classes there, so we call it a classification model. So all regression means is that there is not a fixed number of classes. The output is like a number of some sort, and it belongs in a number line, basically, and it could be like literally any number. It's not a fixed set of numbers. So if you wanted to make an AI model that predicts how tall someone's going to be based on, say, their current weight, their current height, and how tall their parents are, or something like that, right? Whatever features we think are relevant, that output number exists on like some scale, like some infinite scale, right? We can't really obviously we could say like it's unrealistic for someone to be past some certain height, right? But in general, the output is some number, and it could have like some number of decimal places. It's not really belonging to some like fixed set of classes, like 2 classes, 3 classes, 5 classes. So that's all the regression part means. Now let's get into what the linear part means, and this is probably the more important part. So when we're building our model, right, our AI model is going to make some kind of prediction, right? That's what AI and linear regression is for. And all we're saying in the linear part is that the relationship between our data points and the actual answer, let's say like going back to the height example, we have those 3 pieces of information that might matter and the corresponding output, like the actual true answer for how tall someone ends up being. This is all we're saying when we say linear. We're saying that the function is going to look something like this. It takes in 3 things, x, y, and z, the 3 numbers we talked about earlier, and we just multiply each one by a weight. So w1 times x plus w2 times y plus w3 times z. And we might add a constant called a bias. And you can think of that as like the b in y equals mx plus b. Linear regression is basically doing y equals mx plus b, but for as many input attributes as we want. So when we say we're doing linear regression, all the linear part really means is we can't really square anything here. We can't put like a cosine. We can't send that x into like a cosine or a logarithm. The only thing we're allowed to do is multiply our inputs by like w's and add constants. And over the course of something called training, which is going to use an algorithm called gradient descent, when the model actually improves over some number of iterations, all we're doing is at each iteration, we're going to adjust what w1 is, what w2 is, what w3 is, and what b is. And hopefully at the end of some number of iterations, the model is like a pretty decent way to predict how tall someone's going to be. So for a new person that comes along, you could send in x, you could send in their y, you could send in their z, like those 3 pieces of information about them, which is essentially like their weight, their current height, and how tall their parents ended up being. And hopefully this model will give a decent prediction for how tall that person ends up being. So you can kind of think of W1, W2, and W3 as these weights that kind of factor in, okay, how important is X into actually predicting how tall someone's going to be? Is it an important factor? If W1 ends up being a bigger number at the end of training, then the model is basically saying, hey, X is actually pretty important for figuring out how tall someone's going to be. And then same thing for Y, the W2 for Y, same thing for W3 for Z. And then B is kind of just like an extra additional factor that the model might sometimes need to add in, right? So let's say even after you factor in W1, W2, and W3, let's say for every person, there's some like base height, right? Like there's no one who's gonna ever have a height of 0, right? no one's ever going to have a height of 0. So there has to be some base. B is some number that's greater than 0, right? So we always might just add in some base factor there. And then the model will actually learn the value of B over training as well. And this is all linear regression is. Now let's go over the pseudocode for how this would actually work. So let's say we had some function for training a linear regression model and actually learning what those W1, W2, W3, and B are. This is what it would look like. So we would do like for some number of iterations, right? So for some number of iterations that is kind of decided beforehand, right? The more iterations you do, generally the better your model is going to be. There's some exceptions to that, which we can talk about later. At every iteration, what you're going to do is based on your current W1, W2, W3, and B, you're going to do something called get model prediction, which I'm just kind of going to leave as a black box for now as to how we would exactly implement that. But what this kind of subroutine should do is for every example in your data set, right? Let's say you have n training examples in your data set, n people for which you have those 3 pieces of information and you have the corresponding label, like what their ultimate height ended up being. Based on what your current weights and bias is, you should figure out what the model's current prediction is, right? And hopefully this prediction gets better as we do more iterations. Then we are going to do something called get error, right? So if we have the model's prediction and we have the actual right answer, we should be able to get an estimate of what our model's current error is, right? Because the hope is that the model has as low error or loss, as they sometimes call it, as possible. Then the next step we're going to do is something called get derivatives. And here's where it's going to be really important to be familiar with something called gradient descent, which I have a video about on this channel. And this is how we actually optimize our models to minimize that error over some number of iterations. Basically, this function is going to do some little bit of ugly math. Don't worry, you rarely ever have to do it by hand as a machine learning engineer or data scientist or even for side projects, but this function is going to do some calculus actually and calculate some derivatives. And essentially the final step is going to be update our weights. Update our weights. So based on those derivatives that we calculated, let's kind of change, and the error of course, let's change W1, W2, W3, and B to hopefully get a little better. And as we do this over some number of iterations, the hope is that this error goes very close to 0. So this is the rough idea of linear regression. So just one small thing we have left to explain. When I said that we would be calling some function called getError at every iteration, I wanted to clarify what error we're using. So what we use is something called mean squared error. And the formula looks kind of ugly, but we'll break down exactly what it's doing. So all we're doing is for every n of our n training examples, right? We're going to kind of iterate over those examples. And for every example, let's get the difference between what the model's prediction was and the true answer from our data set. And for every one of those, why don't we square them, add them all up for every single example, and then just divide by n. So just taking the average, right? So there's kind of 2 things to understand here. One is why are we kind of adding them up and dividing by n? Well, if we take the average error, then that way our error isn't really dependent on the number of examples in our data set, right? So it's just kind of a rough, like kind of approximation of how poor our model is doing at the moment, or as it goes down, how well it's doing, right? The second thing is, why are we squaring it, right? Why are we squaring the error for every example? Why not just do something like this for every single example? What if we just did the following? What if we just did the absolute value of the prediction at I minus the truth at I, so the absolute value of it, and then divide by n, right? Just taking the absolute value of that difference should kind of give us a gauge of the error of the model, right? But the reason we don't do that is, if you remember from calculus, the absolute value function has some issues with its derivative. It's not super important to get deep into that for understanding machine learning, but that's essentially the reason why we just square it, right? Because squaring kind of gives us that same idea, right? Whether the error was negative or positive, whether prediction was less than or greater than truth, all we really care about is the difference, right? So squaring kind of gets rid of that negative, and turns out it works better than absolute value. One final thing before you basically have all the information you need to code this up. When we actually implement this in code, we use like vectors and matrices to do like the multiplications and additions we talked about earlier. let's say we have our weights in a vector right here, and we have the data point for like one person, their x, y, and z right here. If you do a dot product, which just means multiplying x by w1 plus y times w2 plus z times w3, that gives us the exact model prediction, right? So then let's say we had a data set of a whole bunch of people, right? N people. So that's over here. And this is going to be an n by 3 matrix. So you have x1, y1, z1. This is kind of x, y, and z for person number 1. And then in the next row, you have the second person in our data set, right? So you have their x, their y, and their z, right? And this kind of keeps going on for the n number of people. So all the way to the nth row using one indexing. So y, n, z, n. Then if you did the same thing again, multiply by a 3 by 1, 3 by 1, 3 rows, 1 column, yep, w1, w2, w3, well, what's the result, right? It's an n by 1. So that's n rows, 1 column. And for every single one of our n people, we have their prediction, the model's prediction. So that's kind of an efficient way to do it for n people without a loop, right? You can just do a matrix multiplication, and it turns out a bunch of like libraries have really efficient matrix multiplication algorithms. So that's why we like to kind of vectorize and put things into matrices whenever we're doing machine learning, whenever possible. And if you actually remember how to do the matrix multiplication, it's not like super important. It'd be like this row times this column, right? And that would be the first entry in this vector over here. Then for the next person, it would be their row, again, times this whole column, dot producted, right? And that's the next number over here. So doing this for all the people is essentially like doing get model prediction, what we did over here, for each and every person, except it's a lot more efficient. And this is basically all you need to know for at least the forward pass of linear regression. So feel free to try out the code now.